Hello all. So welcome to this new video in this course on time series forecasting and modeling using R. So just to give you a short background as to what happened in the last session is that we were talking more about a few of the plots which try to measure seasonality, right. So we started with a few examples showing what exactly do you mean by seasonality, and then towards the end we saw some plots of kind of capturing seasonality visually. And there if you noticed we talked about all these kind of plots. So the first one was, let's say, a seasonal plot, right, and then the second one was called as a seasonal sub series plot, right, etc. Okay. And then each plot has its own advantage and disadvantage. So probably initially in today's session we will talk about one more very interesting plot and then we can move on. So I thought of maybe I could draw the plot rather than showing you the actual plot, alright. So this plot is called as individual box plots as per seasons. So what we have is that again we have x axis and y axis, right, and then let's say again on the x axis we have the months, alright, something like that, and then on the y axis we have the actual time series values. Now typically as we have seen in the previous plots also, so be it seasonal plot or seasonal sub series plot, right, etc. On the x axis what we had months, right. So let's say if you have monthly data, something like that, so January, February and then March all the way up to December. So last one is December, right. Now how exactly did you create the seasonal plot? So if you remember, seasonal plot is nothing but for each particular year we kind of have values like that. So let's say one year one can see a pattern like that, in the next year one can actually see a pattern like that, right. So one can actually draw the individual patterns corresponding to each year over all the months, right. So this is a typical seasonal plot, right. So if you erase this, then the next one was called a seasonal sub series plot. So there what we had, if you remember, is in a particular month we had individual kind of line plots for a particular month, right, something like that. So these line plots kind of tell you the extent of the data in that month over all the years, right. So for example January, so January what happens is, let's say this is the minimum value across all the years in January and this is possibly the maximum value across all the years in January. So if you remember the airlines passengers data, so the data ranged from 1949 to 1960 typically, right. And then during January, if you look at the number of airline passengers which travelled in January in each of the years from 1949 to 1960, this is the extent of that line plot, right. And a seasonal sub series plot, there is one more slightly added advantage, is that one can actually plot the mean also using a blue line. So let's say if you draw a blue line something like that here in between somewhere, so this horizontal shorter line kind of captures the mean. So this is a very typical seasonal sub series plot, alright. So now what we will do is we will try to understand one more plot which is called as individual box plots as per seasons, alright. So individual box plots as per seasons. So the idea is kind of very clear here, is that given any month I can actually create some box plots for that particular month. So let's say this would be my box plot for the month of January, this might be the box plot for the month of February, right. This might be the box plot for the month of March, etc. And then towards the end, similarly, this might be the box plot for the month of December. Now again, why is such a plot again important and then valuable is that box plot in itself tells you a lot of things, right. So the extent of this box plot, so these are called as whiskers of the box plot, by the way, and then you have the actual box, right. So the whiskers kind of extend to, let's say, either the minimum or the maximum of the data, something like that. And then the box itself kind of extends from Q1. So Q1 is the first quartile all the way up to Q3. So Q3 is the third quartile, right. And then in between all these boxes we can actually create the medians also, because Q2 is nothing but the median which is given by all these horizontal lines. So let's say this is exactly where my Q2 lies, but then Q2 is nothing but median. Okay. So a box plot in itself kind of tells you a lot of stories about how the data is spread, or where exactly the quartiles are lying, or where exactly the median is lying, right. And on top of that one can actually again get an idea about the extent of all the values for a particular month over all the years, right. So I will say that this kind of a graph or this kind of a side by side box plot for each month over different years is kind of similar to a seasonal sub-series plot. The only difference is in a seasonal sub-series plot, you draw a typical line along with the average, something like that. But then here we are actually incorporating much more information by drawing individual box plots there. Okay. So again, the idea is that one can actually pick and choose to their liking as to which plot should one draw, but then the more information a particular plot is kind of able to convey, the better it is. Okay. Alright, so now we will kind of shift attention from seasonality to another aspect of capturing non-stationarity, which is called as cyclical variations or cyclicality, right. And then in a short time we will kind of differentiate between seasonality and cyclicality. So even though they may seem similar, so seasonal variations and cyclical variations, but then you do have some subtle differences, alright. So firstly, what exactly do you mean by cyclical variations? So cyclical variations are gradual, relatively long term, and then up and down kind of irregular repetitive movements of a time series, alright. So this definition has lot of individual pointers. So let's say cyclical variations are gradual, relatively long term than seasonal, and then up and down irregular and repetitive movements of a time series, okay. Second point is that the data shows rise and falls which are not of a fixed frequency. So again, if you remember when we talked about seasonality, all the variations or all the fluctuations were of fixed frequency, right. So again, if you remember a typical temperature plot. So how does a typical temperature plot look like? So it could be something like that, right. So all these peaks and all these troughs are repeating themselves at a fixed frequency. So difference between any two peaks or the difference between any two troughs is kind of similar roughly, right. But when it comes to cyclical variation, this is not the case, right. So distance between the first peak and the next peak or the first trough and the next trough may be irregular, alright. And the third point is that the period usually extends beyond a single year. So again, if you remember in seasonality, we had the period to be less than 1 year, right. So again, in a temperature data, one can actually see repetitions which are happening in the same months in different years. So period does not extend beyond 1 year, right. But when it comes to cyclicality, the period usually extends beyond a single year. Okay. And then you have like 6 phases in any cyclical variation as follows. So expansion, peak, recession, depression, trough and recovery. So any cyclical variation or any cyclical pattern over several years, let's say 10 years, 15 years, 20 years, right, would be comprising of all these 6 stages or all these 6 phases. So expansion phase, peak phase, recession phase, depression phase, trough phase and then recovery phase, right. Now again, probably in the next slide we will kind of elaborate a bit more on all these phases and then what exactly do you mean by all these individual phases. Alright, so the graph that you see in front of you kind of beautifully demonstrates the 6 phases of a business cycle. So typically one can observe cyclicality or cyclical variations in a business cycle. So let's say you have a business, so business might be in a boom or business might not do that well, right. So all these kind of indicate, let's say, peaks or troughs or periods of recession or periods of expansion, etc. Okay. So initially, let's say the business cycle is expanding and then it expands to the peak, right. So when the maximum is attained, so this is the peak, and then from the peak when it kind of comes back to the zero line, it's called as recession, right. So recession means that business cycle is not performing that well. So it's going on a downward kind of a path or trajectory. And then if it again continues to kind of behave in that same manner, going down in a downward trajectory, then it's called as depression. And then the trough is attained, and then once a trough is attained of a business cycle, then again starts to recover. So recovery phase, and then the same thing repeats, alright. So expansion, peak, recession, depression, trough and recovery. And once this recovery stage is attained, now again the second cycle would begin, alright. So this is a typical cyclical variation of a business cycle. Now let's look at a few examples and then we'll try to differentiate between cyclicality and then seasonality. Alright. So let's say the first example could be business cycles. So you talk enough about business cycles. So let's say economic expansions are followed by recessions. So typically something like this. So if a business cycle is expanding, it attains its peak and then the recession starts. So So, something like that, right. Let us say this is the horizontal line, and then once the recession has kind of reached the 0 stage, then again what you can do is you can again come down. So, let us say it attains a trough and then again comes back, so something like that. Okay. So, this is a very typical business cycle. Then one more example could be price cycle. So, prices of let us say some commodities might as well behave like that. So, let us say the prices are expanding, then the prices reach its peak, right. Then once the prices reach its peak, then again they start a downward trajectory. So, this is called as recession, then depression, then trough and then recovery, alright. So, when future production decisions are based on current prices. So, let us say based on current prices, if you want to kind of predict what would happen in the future in terms of production, then this is a very typical price cycle, right. Or one can actually observe some cyclical variations in natural phenomena. So, let us say solar cycles, because what happens is sun's magnetic field undergoes a cycle after approximately every 11 years, right. So, the magnetic field of the sun itself kind of behaves in a cyclical manner and then sort of repeats after every 11 years. So, after every 11 years what typically happens is that the north and south poles of the sun kind of exchange their position. So, they shift entirely, alright. So, it is kind of a similar idea as to a business cycle or a price cycle. So, let us say when the north pole is towards the north or in one direction, right, then the stage could be of expansion stage, and then probably when it starts flipping, then we can actually attain a kind of a recession stage, then probably depression stage, and then again a recovery stage, alright. So, all these are few examples of where one can observe cyclicality or cyclical behavior in let us say natural phenomena or price data or let us say business cycles and so on. Yeah, so now talking about the sunspot data. So, the very typical sunspot data. So, what you observe here is that let us say this is the behavior of sunspots. So, if you observe on the surface of the sun, you have these dark spots, right, and then those dark spots are called as sunspots. And then ideally, so understanding or analyzing the number of sunspots appearing on a daily basis or monthly basis, right, is kind of important because that decides on the magnetic field of the sun, alright. In any case, so let us say this is exactly how the sunspot data behaves. So, the yellow line is the daily observations, the blue line is the monthly data, and then the red line and possibly towards the end here are the forecasts and the fitted model, alright. So, how exactly a particular fitted model behaves, but then the actual data is given by yellow and then blue, right, and then even here you can see a same typical behavior, right. So, let us say the number of sunspots they are growing here, then they start falling, right, and then this might be a recovery phase where again it starts to pick up and then possibly it will again come down. So, again the number of sunspots kind of behave in a cyclical manner. And then here I am using some images which are due to all these kind of citations. So, if one is really interested as to what do you exactly mean by sunspots, so how are sunspots measured and what is the use case of doing all that. So, one can actually refer to all these links by the way. Okay. Alright, now the important and pressing question is what exactly is the difference between seasonality and cyclicality, right, because again in seasonality we have repetitions, in cyclicality we again have repetitions. So, what might be the difference? Okay. So, if the fluctuations are not fixed or they are not of a fixed frequency, then you have a cyclical variation, right. So, something like this. So, let us say if you draw a random graph and if the repetitions are not of the fixed frequency. So, let us say the next one could be something like that, then possibly the next one is like that. So, even though you have peaks which are here, here and there, but then those are not of the fixed frequency. So, this is a very typical graph of a cyclical variation pattern, right. On the other hand, if the frequency is unchanging or unchanging means fixed. So, if the frequency is unchanging and related to some calendar effect, it is called as seasonality. So, temperature data, rainfall data, data due to holidays, so sales during Diwali, etc. So, all these examples are seasonal examples. Okay. And typically the average length of cycles is much more longer than the seasonal patterns. We have seen that, right, because a typical business cycle does not end within a year, right. So, it might take, let us say 10 years or 15 years or 20 years to complete one business cycle, comprising of all the 6 phases that we saw earlier, right. So, the average length of cycles is much longer than the typical average length of a seasonal pattern. And last one is magnitudes of cycles are more variable than the seasonal patterns. So, the amount of variation in the peaks or amount of variation in the troughs are much more variable in a cyclical pattern than the seasonal pattern. Right. So, these are some of the differences when it comes to understanding the ideas behind seasonality, cyclicality, because even though these two are non-stationary aspects, they mean entirely different things. So, how do you measure seasonality? How do you measure and capture cyclicality? So, you have to kind of come up with slightly different ideas. Okay, so probably what we will do now is we will shift attention to a slightly different kind of an angle, and then we are almost there towards defining that Sarima model and then understanding a few more aspects about non-stationarity. Okay. So, firstly we will try to understand as to, in time series literature you have a thing called as unit root, right. So, what exactly do you mean by unit root? Okay. So, let us say consider a model. So, maybe you can pause the video for a minute or something and then try to identify this model. So, we have discussed this model number of times. Okay. So, this model is a typical ARMA model, is not it, because this is the autoregressive structure, this is the moving average structure. Okay. So, this model could be a typical ARMA kind of a model with what orders? So, since it goes back to t minus 2, so the autoregressive order could be 2 and then the moving average order could be 1. So, this is an example of an ARMA 2-1 model. Okay. Now, if you focus on the left hand side of this equation, of the above equation, so what do you observe? So, I can actually write down the equation in this polynomial structure. Now, again what exactly is B here? So, B is nothing but the backshift operator, alright. So, B is nothing but the backshift operator. So, if you operate B on yt, this gives you yt minus 1, alright. So, B is the typical backshift operator which we studied in one of the previous lectures, alright. So, again if you focus more on the left hand side, this is exactly how you can rewrite the equation, isn't it? Because I can actually combine the coefficients. So, 1 minus 1.9 into B plus 0.9 into B square applied on yt. So, this entire thing is more like an operator applied on yt, alright. Now, if you decide to solve for such an equation, so you take this operator as it is, so 1 minus 1.9 B plus 0.9 B square equal to 0, right. So, it so turns out that the roots of this equation are of interest to us. So, what exactly are the roots of this equation? So, one can use any calculator or try to solve this using pen and paper and then find out the answer. So, the roots of this equation are 2 because you have a quadratic equation. So, there should be 2 equations, right. So, the roots are 1 and 10 by 9, and here if you notice one of the roots is exactly equal to 1. So, whenever such a thing happens, we call that root to be a unit root. Okay. So, we hence have a unit root. So, whenever one of these roots is 1 or whenever one of the many roots, because this can be extended up to many more lags, right, depending on this autoregressive order, right. So, if one of the roots of many such roots of this typical polynomial happens to be 1, so that root is called as a unit root. Right. Now, why exactly studying unit root is important and so on? So, we will study in the next slide. Right. Okay. So, firstly unit roots make a process non-stationary, but then exactly why? Right. So, however, if you assume let us say a WT which is a difference process. Okay. So, unit roots make a process non-stationary to start with. So, whenever you observe a unit root as one of the roots of that equation, you can actually say that the process is not stationary, right. But why exactly? So, let us say the initial process yt is non-stationary. So, yt has to have one unit root. Okay. However, if you assume the differenced process, so let us say Wt is what? So, Wt is nabla operated on yt. So, you are differencing it once. Okay. So, essentially what we are doing is we are getting this. So, again if you go back one slide, so we started with this model right here in terms of yt. Okay. And here if you apply differencing 1, so if you kind of calculate something like that which is nabla yt, which is of course Wt as per our notations, then eventually you end up getting this equation, alright. And then this is nothing but a stationary ARMA 1-1 process, make sense? And hence we argued that the initial process yt, right, that the initial process yt follows an ARIMA process with 1, 1, 1. Okay. So, initial process yt happens to be ARIMA process 1, 1, 1. Okay. And why exactly? Because you are differencing it once and you are getting hold of a stationary ARMA 1, 1 process, right. So, the original process has to be ARIMA 1, 1, 1. Okay. And since in the original process you had a unit root, right. So, unit roots kind of make a process non-stationary, because ARIMA process is an example of a non-stationary process to start with. Okay. Alright, now the end story is, why is a unit root a problem, right. So, what one can do is, unit roots kind of imply the following model structure. So, whenever you encounter a unit root, I can actually write down this equation, and what exactly is the equation? So, 1 minus b is the backshift operator applied on yt, right. So, if you expand this, what will you have? This is nothing but yt minus 1 equals some function of white noise terms or some function of error terms, right. So, ETs are nothing but errors, right, in our notation. So, let us say if yt minus 1 is a pure function comprising of some errors, right. So, f of et is what? F of et is some function of error terms. This implies that the current value, which is yt, is same as the past value plus some white noise term or some white noise structure, right, because yt would be what? So, yt would be yt minus 1 if you take this on the other side plus function of errors. So, what do you mean by that? So, thus in the long run the process will never converge to any mean, right, and hence which means that the process is in fact non-stationary. So, in the long run, if the process does not converge to a particular mean, right, so we can actually say that the mean is changing or mean kind of depends on the time, right. So, under all these assumptions we can actually say that the process itself is not stationary. Okay. So, whenever you have a unit root in that polynomial structure or in that polynomial equation, if you observe at least one unit root, then the process has to be non-stationary because of this simple reasoning, because the current value depends on one past value through some errors. So, the current value is the past value plus some random errors, right, and then what exactly those errors would be, nobody knows, right. So, past value plus a bunch of errors is giving me the current value. So, in the longer run it would never converge to the mean, because the entire process depends on those random errors, okay, and hence the unit root is a problem. Okay. So, now we are at a stage where one can actually define the causes of non-stationarity, right. So, any practical time series can be non-stationary because of the following reasons. So, the first one is presence of unit roots, right. So, we argued a short while back as to why that is a problem, right. Then the next one is presence of a deterministic polynomial trend, right. So, deterministic polynomial trend means what? So, the time series has some trend and then that trend aspect is deterministic. You can actually determine the exact model of that trend or the exact structure of that trend, okay, or the presence of some stochastic trend. So, stochastic trend means the trend depends on time, alright. So, such a trend is called as a stochastic trend. So, trends could be of two kinds. So, deterministic or stochastic, alright. So, these 3 points kind of amount to non-stationarity in the time series. Okay. So, now the last section of this lecture would be, we will discuss some tests for stationarity. So, are there some hypothesis tests or can we perform some hypothesis testing kind of a scenario or situation to kind of test out if a time series is indeed stationary or not. Okay. So, in literature different people have come up with their own tests. So, for example, the first one is called as augmented Dickey-Fuller or in short ADF, right. So, augmented Dickey-Fuller test or in short ADF test. So, typically what this test does is that it sort of tests if a unit root is present in the time series or not. Okay. So, this ADF test kind of tests if a unit root is present in the time series or not. And a short while back we have seen that if there is a unit root, it kind of implies non-stationarity, right. So, whenever you have a unit root in the polynomial equation there comprising of the backshift operators and so on and so forth, then this kind of implies non-stationarity. All right. So, what exactly the hypothesis here? So, the null hypothesis is the series is not stationary, whereas the alternative is the series is stationary, right. So, for some reason if you reject the null, so what do you mean by that? So, if you apply this ADF test and you reject the null hypothesis, so it means that the series is in fact stationary, right. So, if you reject the H naught or if you reject the null hypothesis, it means that the series is in fact stationary. Okay. So, and all these tests by the way can be performed in any software including R. So, you have a function called as adf.test, right. So, during one of the practical sessions we will take it up, but then just to reference it here. So, if you apply this adf.test on any time series, so let us say your data could be temperature data, just an example. So, let us say adf.test applied on temperature and then it will give you a p value, right. So, any ADF test if you are using in a software produces a p value and then you can compare that p value with the significance level. So, if the p value is less than alpha, then you reject the null, otherwise you fail to reject the null. Make sense? So, the first one is called as ADF test. Then the next one, the name is slightly difficult, so even I won't pronounce that. So, in short is called as KPSS test. So, KPSS are short forms for or initials of 4 people, okay. And then they produced a test as a combined kind of a research paper. And then what exactly is this test? So, this tests the null hypothesis that a time series is stationary around a deterministic trend or mean against the alternative that it is non-stationary. So, idea of ADF test was for checking unit roots, while the idea here is to check for a deterministic trend component. Okay. And then the null hypothesis is series is stationary, alternative is series is non-stationary. Okay. So, this is the KPSS test. Then the next one is Phillips-Perron test or PP test. Okay. So, this is kind of similar to the ADF test, but it makes different assumptions about the error terms and is more robust in the presence of autocorrelation and heteroscedasticity. So, this heteroscedasticity means nothing but changing variance. So, this is a technical time series terminology for writing down changing variance. So, changing variance means heteroscedastic, and then if the variance is not changing, if the variance is constant, we call that as homoscedastic. All right. So, again similarly here the null hypothesis is series is not stationary and the alternative is series is stationary. Okay. So, again this PP test is kind of similar to ADF test, but has some different assumptions about the error terms and generally speaking is more robust in the presence of autocorrelation and if the variance is changing or heteroscedastic in nature. Okay. And then the last test is called as variance ratio test. So, what exactly do you mean by variance ratio test? That this kind of tests for a random walk hypothesis indicating non-stationarity, because all of us have seen in previous lectures that any random walk is not stationary, right. So, it kind of compares the given series with a random walk. So, if you see resemblance with a random walk, then one can actually argue that the series is not stationary, right. And then this variance ratio test kind of produces a ratio. So, if that ratio is significantly different from 1, this in fact suggests that the series is not a random walk. And if the series is not a random walk, it means that the series has to be stationary, right. So, the null hypothesis again here is series is not stationary and the alternative hypothesis is that series is stationary. So, essentially through these all different tests, right, I mean ADF test, then PP test, variance ratio test, KPSS test, one can actually perform a hypothesis test, which is a much more formal thing than basically commenting something on based on some graphs and so on and so forth, right. So, if one is able to perform any of the formal tests, ADF or PP etc., then one can actually gain much more confidence whether a series is stationary or not. Okay. Alright, so now probably in the next session what we will do is we will converge to that SARIMA model that we talked about earlier. So, we will kind of define the SARIMA model, we will again link it back to why exactly do you need the extension from ARIMA to SARIMA, right, and then how do you kind of expand that SARIMA model, what are the orders of a SARIMA model, along with some examples. Okay. Thank you.